Good afternoon to all the listeners. My name is Utkarsh, and I will be discussing the fundamental theorem of calculus. So, as we know, the fundamental theorem deals with integral calculus. So, let's first do a recap of integration, integrals, integrability. When we refer to integral of a function f, here as you can see, there is a function fx, f, and it is restricted to the domain, the interval a comma b. What do we mean when we say integral of f over ab? So essentially, we refer to the area under the curve. S represents that area. So I can say integral a to b of fx is equal to S. So essentially, we mean area under the curve. That's what an integral is. But we know that not all functions are integrable. So let's see the notion of integrability. For that, we need to know these terms: partitions, upper sums, lower sums, upper and lower integrals. At first, partition. So can someone recall what exactly a partition is? Am I audible?
Yes, you are. Students, if you have any comment on this, please, you can unmute yourself. Okay.
Anyways, a partition, was there someone?
No. Please continue.
Huh. A partition is a subset of the interval AB only, which is it on which it is defined, such that it is a finite set having, let's say, n numbers, which have a special property. That is, they can be ordered. They are arranged in a certain way, like you can see here in an ascending order, where the first term x naught represents A and the last term xn represents B. That is, it covers both the ends of our interval. That's it. That is a partition. Now coming to upper sums and lower sums. So you can see a graph of a function fx is equal to 10 minus x square. Here we have our domain restricted to 1 comma 2, the interval 1 comma 2, and a partition which has 5 points, x0 to x4. x0 is 1 and x4 is 2. So what actually we want to do is, we know that the integral is the area under the curve. So we want to approximate it, right? We want to find that real number. For that, we will approximate the area. So can you tell me which shape is the easiest to calculate the area of? It's staring at you. Yes, a rectangle. A rectangle is easiest to calculate its area. So being confused mathematician, we will calculate using a rectangle. We will approximate using rectangles. And the partition will help us make these rectangles. So for us to calculate an area of a rectangle, what do we need? We need two things: length and breadth. Can we see the breadth staring at us? Sorry. Like for the first rectangle, which is here in this first picture, from x0 to x1, and we have a rectangle above it. The breadth is the length of the subinterval, right? So breadth is easily determinable because of the partitions. Now I have to see what should be my length, right? We need length as well. So if you can see these two lines in the second picture, I have these many points as my candidates for length, right? And that means infinitely many points. Let's zoom this picture a bit. So we have infinitely many points, but I need to have at only one point, right? To approximate, I need to define it using only one point. What are the three possibilities you see here? There are only three possibilities. Either I can take the highest value, or maybe the lowest value, or maybe something in between. Taking something in between means it is a tedious task. I'll have to define it and do things so that I know it exactly. That's not what I will want to do. So I can either take the highest value or maybe the lowest value, right? So I'll do both. I'll approximate from above as well as from below, right? So what is the highest value actually? Uh, what I mean is, by highest value, what do I mean? What of highest value of what are we talking about? Any guesses? Any answers? So essentially, we are talking about the image set of the subinterval, the first subinterval here being precise, the first subinterval, and under F, the images of all the points under of all the points of the first subinterval under F, and then I am referring to the highest value of that. So what should be the highest value of that? That will be the least upper bound, right? So I can choose least upper bound as my length as well as the lowest value. That must be the greatest lower bound, right? So I can choose any one of them. So how should I define? And this will give me the area of one such rectangle. I have many such rectangles, right? In particular here, we have four rectangles. Then I need to sum all of these, area of all those four rectangles, sum it, then it represents the approximate area under this curve, right? So I want to define my upper sum as UFP is equal to summation I equal to 1 to n mi, that I'm taking as least upper bound of the ith subinterval into the length of the ith subinterval, right? And analogously for LFP, that is the lower sum. So UFP and LFP are symbols for lower sums, and that's how I define it, right? Now, since I can have many such partitions, right? In 1, 2, I can have infinitely many such partitions, right? That means infinitely many candidates for my approximation, for my area, right? But that's too many. I want to take the best one, right? That takes us to upper and lower integrals. So out of all those partitions, out of all those upper and lower sums, I want to choose the best one. What do you think should be the best one? Basically, in upper sums, I am getting a little more area than expected, right? As you can see in this picture, here we have a little more area than what we actually need. And in this another picture, we have a little lesser area, that is for lower sums. So basically, I want to pull down the upper sums a little and push the lower sums a bit. So I want to take upper sums to a lower value. I want to choose I should say, least value out of all the upper sums, right? So if I have the set of all upper sums, reminding that they are all real numbers, what should be my best candidate, or I should say best approximation? That's what I want to call as my upper integral. Any answers? So my best candidate must be the greatest lower bound, right? I'm pulling it down to the least value it can go to, right? And I'm defining my upper integral as the greatest lower bound of all of the set of all upper sums. And similarly for lower sums, for lower integral, I'm defining least upper bound. I'm taking them highest that they can go. right? So we have now two best candidates, two best approximations which we can have for our integral, right? For our area. So what do you think when a function will be integrable? Can you take a guess? When I'll call a function is integrable, we have two approximations. So actually, we call f to be integrable if and only if both the upper and the lower integral coincide. That is, they have the same value. That means they point at the same area, the same s, which is there, which I want to find as my integral. Therefore, now we know the value of the integral as well, right? So when upper and lower integrals are same, they point to the same value, and that same value we are saying we are calling as our integral. That being done, we are done with integrability and integration. Now it takes us to fundamental theorem of calculus, first form. So what does it talk about? You may have noticed that this all integrability and integration was way different than what we did in our school, right? In, in school, we used to have some function gx, and when we integrated it, we calculated a function f, which is maybe can be called as an integral function. And when we used to put values of the limits, so the upper limit value and at the lower limit value, and subtract them, we used to get the area and call it that is our integral, right? So these two integrability notions, integration notions are very different. So that's what fundamental theorem of calculus looks to integrate, basically to connect. So we want to say that both the integration ways are same. For that leads us to two questions. That is, what do I have to prove? What exactly should I prove? And what exactly do I need to prove that? Right? So any guesses? Any guesses? What do I have to prove actually? So actually, what I want to prove is when I approximate my area using this Riemannian way, it must be equal to that Newtonian way, right? That means integral of a to b fx must be equal to some fb minus fa, right? So that leads us, what do I need? That leads us to what do I need? What do I need? First, I need this function f in which I can put values and then check, right? So I need function f first. Then only I can find whether the value, right, fb minus fa, this value. Do we need any condition on f? Any condition that it should follow? Yes, f has to be differentiable. If f isn't differentiable, then f dash x does not make sense. And if it does not make sense, then what will be calculating the area of? What we will calculate the area of under, right? So we need f and we need f to be differentiable, right? Now f is differentiable. That means f dash x exists. Is this enough for our proof? So actually, we want to assume that f dash is integrable on a comma b there, right? Then we want to say something. But can we just let f from a b to r is differentiable? Is it enough for us to say that integral of f dash x from a to b is equal to fb minus fa? Is it? If this makes sense, then what it means is that if f is differentiable, then every f dash is integrable, or gets when it gets integrated, we get a solution, basically an area. Is that true? For every f which is differentiable, f dash is integrable. Actually, not. That's not true for some cases. One of such is Volterra's function. That function is differentiable, but it is not integrable. But the differential of the function is not integrable. So actually, we need integrability as well. So we have assumed two conditions. F from AB to R is a function and is differentiable. Hence, f dash x exists and f dash is integrable. Then we want to conclude that integral of f dash from A to B is equal to fb minus fa. Right? This is what we want to do. Now let's see and make some observations from our previously learned things, and then come and then make a rigorous proof. Right? So when we defined our upper and lower sums, we saw that capital Mi is the LUB of images of the ith interval under F, and similarly small mi is the GLB. Now I want to ask, is there any connection between, sorry, I have a mistake here, between any capital Mi, small mi, and f dash c? I want to ask f dash c. Is there any relation? F dash c is actually an image of C, where C belongs to the ith interval. Mi is our LUB, capital Mi, and small mi is the GLB. Is there any relation between them? Yes, there is, absolutely. By definition, it is. By definition, we know, by definition of LUB and GLB, we know that this particular inequality holds, and it will hold for every C, right? Now I want to ask another question. Is this also true? Can we say this? Yes, essentially, because we are just multiplying a positive real number, right? The length of an interval is positive, and we are multiplying it to each term in this inequality. So yes, this makes sense. This is true. But now, is f dash c into the length of the subinterval xi plus 1 minus xi, that is the length, is it reminding you of something? Is it similar to f dash c into b minus a? If that reminds you something, anyone? Essentially, yes, we have something related to it. When f, the integral, is differentiable, then we can say something about f dash c into xi plus 1 minus xi, where our domain is xi plus 1, xi plus 1. And c belongs to ith subinterval. Yes, actually, by mean value theorem, we can say f dash c into xi plus 1 minus xi is equal to f of xi plus 1 minus f of xi. Maybe it's better to say f dash c into b minus a is equal to fb minus f of a. Let's see what exactly mean value theorem says. Whenever f, a function, is continuous on AB, the closed interval, and f is differentiable on open interval AB, then there exists a point C in AB such that fb minus fa is equal to f dash c into b minus a. Essentially, that means we can find a point such that the slope at that point is same as the line join is same as the slope of the line joining FA, the points A comma FA and B comma FB. That's what exactly mean value theorem means. Hence, now we can conclude that small mi into xi plus 1 minus xi is less than equal to this value which we have got, f of xi plus 1 minus f of xi, which is less than equal to capital Mi into xi plus 1 minus xi. That is, both the other terms are area of one particular rectangle, right? So can you see that if what happens if we do a summation here? So what happens if we do a summation is we will get on both sides a upper sum and a lower sum, right? And in between we get summation of I equal to 0 to 1 to n fxi plus 1 minus fxi. What does it represent? How does it open up? Can someone tell? It's a very nice sum. So actually, it is called a telescopic sum. Telescopic sum, which leads us in which every last term of the next coming terms and the last sum cancel out the next term, right? Which leads us to be left with last two terms. That is, we will be left with FB minus FA. With that being taken as an observation, let's now write a textbook proof of our fundamental theorem. I think we have an idea that we can prove it, right? We have got FB minus FA, which we wanted to see. So let's see the proof. So if you recall my statement, it was that if f is differentiable and f dash is integrable, then integral of f dash from a to b is equal to fb minus fa. So let's first approximate the integral of f dash. So we have taken an arbitrary partition P on A comma B. Then directly by mean value theorem, we can say this will happen for every interval. F dash Ci into xi plus 1 minus xi will be equal to fxi plus 1 minus fxi, right? And for some C, there will exist some C. This will happen for every subinterval. And now, since we have mi less than equal to f dash ci, since ci here is changing as per the interval, which is less than equal to mi, because we want to do the summation. So when we do the summation, we have LFP, the lower sum, which is less than equal to the summation of this middle term, which will be less than equal to the upper sum. Which eventually means LFP is less than equal to summation of fxi plus 1 minus fxi, the telescopic sum, which is less than equal to the upper sum. That is, LFP is less than equal to fp minus fa, which is less than equal to UFP. And since our partition was an arbitrary partition, what can we say? We can say that least upper bound of the LFPs would be less than fp minus fa and would be less than equal to the inequality will hold for least upper bound and the greatest lower bound. Now, I almost have my proof complete. I want to make one final statement. Can someone guess what is it? What actually do I need to state which completes my proof? Anyone? Now we need actually the integrability of f. Because if f is integrable, LUB of lower sums, that is our lower integral, and GLB of upper sum, that is our upper integral, are exactly the same. And since this inequality holds, what can we finally conclude? So since f dash is integrable, the first and the last term are same, right? Then it follows directly because the middle term will also be the same. Hence, integral of a to b, integral of f dash from a to b is same as fb minus fa. That means the Newtonian way of integration is nothing but same as the Riemannian way of integration. That's it from my side.